let's take a look at thermodynamics. So, thermodynamics is the study of how a system will evolve from one state to another. So, for example, if we're looking at an ideal gas, we have the equation of state for an ideal gas. And the equation of state for an ideal gas tells us that if we know the pressure and the volume and the number of moles, then we know the temperature. And if we change the pressure and the volume to a new value and then we still have the same number of moles, we can get the new temperature. So it tells us what the values are, but it doesn't tell us how the system evolves from the original state to the other state. That's what thermodynamics does. And we're going to approach thermodynamics from a systems view. So imagine that we have a system right here in this little box, and then we have an environment around it, surrounding the system that we're looking at. We're going to define closed systems and isolated systems. Closed systems are those where the mass and the material within the system does not change. So we have a fixed mass and we have a constant value of n and a constant value of n. An isolated system has fixed mass, so same as a closed system, but in addition, no energy is exchanged with the environment. So in that situation, we have constant, say, mass, n, n, and a constant internal energy. So let's look at the first law of thermodynamics. And by the way, there is a zeroth law of thermodynamics, a first law, a second law, and a third law. So we say there are three laws of thermodynamics, but there's actually four of them because of that zeroth law. It's a weird method of counting. Don't worry about it. It has to do with the history of it. Whatever. We're going to look at the first law right now. So conservation of energy tells us that the total internal energy of a system can only change if energy is transferred in or out of the system. We saw this idea with energy balance. So we can write this down as an equation. The change in the internal energy of a system is equal to the energy in or out from thermal energy transfer plus the energy in or out from work that's done on the system. Okay. So we can write this down in letters. The change in the internal energy of a system is equal to Q. So Q is the thermal energy that's exchanged in or out of the system, minus W, where W is the work that's done. Now, in order to use this equation, we have to agree on a few things. So the change in the internal energy, that kind of makes sense, right? We don't really have to worry about that. We know what the change in the internal energy means. The Q, however, the Q is the thermal energy transfer. If we have a positive Q, we're going to have that mean that thermal energy was transferred to the system. If we have a negative Q, we're going to have that mean that thermal energy was transferred out of the system. When we talk about the work, if the work is positive, we're going to take that to mean that the system does work or adds energy to the environment. And if the work is negative, then that means the environment does work on the system. This is called the Clausius sign convention. All of this together, these accepted uses of positives and negatives for Q and for W, the Clausius sign convention. And what we can do is rearrange this, and we can say that Q, the thermal energy transferred in or out, is equal to the change in the internal energy of the system plus the work done. This is a statement of the first law with the Clausius sign convention. And we can draw a little diagram of what we're talking about here. So here's our system. It's got an internal energy U. If there is a positive Q, then thermal energy is being transferred into the system. If Q is negative, then thermal energy is being transferred out of the system. If we have a positive work, then the system is doing work on the environment. So that means that energy is exiting the system. And if the work is negative, then work is being done on the system, which means that energy is being added into the system. Now, we often look at what's called a PV diagram here, pressure versus volume diagram. This is also called an indicator diagram in engineering sometimes. So we're going to imagine that we have a system and it goes from a state here to a state here. And it travels along this line to go from one state to the other. So if you look, what's really happening then is the pressure is remaining constant and the volume is increasing. So if we draw a little diagram, let's imagine we have a cylinder right here. The cylinder is going from a state right here with pressure P, and let's call this an area A, and it's got a volume V, and it's expanding at a constant pressure. So say it expands by some length, delta x, right here. So the volume increases by some amount. Say it increases to V plus delta V. So what happened here is the cylinder pushed on the environment. It did work on the environment. And work, remember, work is equal to Fs cosine theta. In this situation, the theta here is 0 degrees because the force that was applied to that top as it expanded was in the same direction as the displacement. So really, the work here is equal to F times delta x. So the work can be written as pressure times area. That's the force, right? Force is equal to pressure times area times delta x. Well, wait a minute. Area times delta x, that's the change in the volume. So the work here is equal to the pressure times the change in the volume. And it's a positive value. It has to be a positive value because work was done on the environment. If we had a similar situation where the cylinder became smaller and it went from, say, a large volume to a small volume in that direction on the diagram, then it would be negative work because work would be done on the system rather than on the environment. So, one thing to notice, and this isn't exactly a proof, but it is true. In a PV diagram, work is equal to the area under the curve. So, in our initial example, here's the initial state, there's the final state. That's the area under the curve. And the area under the curve here is positive because the volume increased, went from here to there. If the volume decreased, if we went from right to left in the diagram, then the work would be negative. And also, even though in our diagram we had this sort of simple shape, this box here, this rectangle, it doesn't have to be. If we had a situation where the system evolved from here to, say, there, then it's still true that the work that is done is the area under the curve. And if the system evolves to a larger volume, it's a positive work. And if the system were to evolve to a smaller volume, then it would be a negative amount of work.